What if the universe has already shown us something impossible, and we've been staring right at it all along? Tonight, we journey to the edge of what science can explain, where the laws of physics begin to blur. Welcome to Cosmic Drift. Imagine covering 1 square meter above the clouds of Uranus with an invisible accounting frame. Sunlight enters, heat leaves. For almost 40 years, the most familiar version of the story said the book's nearly balanced, with almost nothing coming from inside the planet. Then astronomers rebuilt that ledger across Uranus's full orbit. The result changed one of the solar system's oldest mysteries. Uranus is not heatless. It gives off roughly 15% more energy than it receives from the sun. That extra energy has to come from within. It is a small surplus beside the total flow of sunlight and infrared radiation, but it is not zero. The surprise is what happens when the same accounting frame is placed over Neptune. Neptune's internal heat flow is not a little larger. It is roughly 5 times larger. These planets are close in size. They formed from the same young solar system. They are usually filed under the same name, ice giants. Yet one leaks ancient heat at a restrained rate, and the other releases it far more freely. So this is no longer a story about a planet with no heat. It is a story about twins that may never have been twins at all. The first reward is already in our hands. The old claim that Uranus gives off no internal heat is obsolete. The modern measurements do not merely add a decimal place, they change the question. For Uranus, the current estimate of internal heat flow is about 0.078 watts through each square meter of the planet's effective radiating surface, with an uncertainty of about 0.018 watts. Neptune's corresponding estimate is close to 0.4 watts per square meter. Those are not the only numbers used in every model, but they make the contrast plain. Put 5 Uranus tiles side by side, and together they release about as much internal heat as 1 Neptune tile. This is not the kind of heat that would warm your hand. At Uranus, the internal part is less than the power drawn by a small light on each square meter. But a planet has billions upon billions of those square meters. Add them across a globe almost 4 times the diameter of Earth, and the quiet leak becomes a record of energy stored over the age of the solar system. That is what makes the comparison so useful. Heat is not just temperature. It is history in motion. Every giant planet formed by gathering material that fell into a deepening gravitational well. Collisions, compression, differentiation, and the sinking of heavy material converted motion into internal energy. Some of that energy escaped early, some remained. Radioactive elements in rock added a smaller, continuing source. Over 4.5 billion years, the planet's interior and atmosphere decided how quickly that energy could find its way back to space. The outward flow we measure today is the last visible stage of that long negotiation. If you like following a mystery from the measurement to the honest edge of what we know, subscribe. That is the journey we make here. Now look again at the 2 blue planets. The important word is not cold. Both are cold at their cloud tops. The important word is cooling. Neptune is still losing internal energy far faster than Uranus. Either Neptune began with a different store, Uranus became unusually good at holding its energy down, Neptune became unusually good at moving energy out, or several of those things happened together. Each possibility leaves a different trail. A violent collision could have rearranged Uranus. A quiet layer deep inside could be slowing convection. Condensing material in the atmosphere could alter how heat is carried upward. The planets might have formed at different times, from different mixtures, or in different parts of a migrating outer solar system. These are not interchangeable stories. They make different predictions about gravity, magnetic fields, atmospheric composition, moons, rings, and how the heat changes with latitude and season. That gives us a way through the uncertainty. We do not have to choose the most cinematic explanation. We can ask what each explanation would require the planets to be. But before we descend into either world, we need to understand the ledger itself. The difference between sunlight and internal heat sounds simple. For a distant planet, it is one of those measurements whose final line is easy to read only because years of difficult work have been hidden above it. Stand outside Uranus with our imaginary square meter frame. Energy arrives mainly as sunlight. Some is reflected by bright clouds and haze. The rest is absorbed by the atmosphere and deeper layers. Energy leaves mainly as infrared radiation, the long wavelength glow emitted by any object above absolute zero. If the outgoing thermal energy exactly matched the absorbed sunlight, the global budget would show no measurable contribution from inside. If the outgoing energy is larger, the remainder is called the internal heat flux. The equation is short. The planet is not. Uranus is a rotating sphere with bands, clouds, haze, seasons, and an axis tilted almost onto the plane of its orbit. One pole can face the sun for decades, while the planet continues around its 84-year path. The sunlight received at the top of the atmosphere changes with distance. The fraction reflected depends on wavelength, cloud structure, viewing angle, and season. The infrared output must be measured across wavelengths and across enough of the disk to estimate the whole globe. Then both flows must be averaged over time. The modern Uranus result came from assembling that larger view. One analysis estimated that the planet absorbs about 0.604 watts per square meter from the sun, with an uncertainty of 0.027. It estimated outgoing thermal radiation at about 0.693 watts per square meter, with an uncertainty of 0.013. Divide the second by the first, and Uranus emits about 1.15 times what it absorbs. The values are close enough that uncertainty matters, but far enough apart that the internal contribution now emerges as a positive result. Another analysis approached the same energy balance with its own treatment of reflected sunlight, thermal emission, and orbital averaging. It arrived at an internal flux near 0.078 watts per square meter. The overlap between these independent approaches matters more than a perfectly matching last digit. Both move Uranus away from zero. This is how a planetary fact changes responsibly. Not because one dramatic picture overturns the past, but because different measurements and models begin pointing across the same boundary. There is an important subtlety here. Astronomers are not seeing a labeled stream called internal heat. They are measuring large terms and taking a difference. That makes error bars part of the fact, not a footnote attached after it. Imagine weighing a person while they hold a suitcase, then weighing the person alone, and trying to recover the suitcase's mass from the difference. If both scale readings are uncertain, the suitcase value inherits both uncertainties. Uranus is harder. The sunlight and infrared measurements were not collected by one perfect instrument at one perfect moment, and the planet changes with season. So when we say Uranus emits roughly 15% more energy than it absorbs, roughly is doing real work. It protects the conclusion from false precision without weakening it into vagueness. The corrected budget gives us a completed result. Internal heat is present. It does not give us a map of where that heat originates, the route it follows, or whether every latitude releases it at the same rate. It also does not tell us that Uranus suddenly became warmer. The planet did not change when the analysis changed. Our accounting did. That distinction will matter again and again. A new result can transform the scientific mystery, even when the physical world has been doing the same thing for billions of years. The next question is why the old near-zero picture held such authority. The answer begins with a machine that left Earth in 1977. Voyager 2 was built for Jupiter and Saturn, with the possibility of continuing outward if the spacecraft, funding, and celestial geometry allowed. After its Saturn encounter, engineers guided it toward a planet no spacecraft had ever seen closely. On January 24, 1986, Voyager 2 passed Uranus at a closest distance of about 81,500 kilometers above the cloud tops. At interplanetary scale, that is an intimate encounter. The spacecraft returned images of rings and moons, measurements of charged particles and magnetic fields, atmospheric data, and the first close thermal view of the planet. The encounter was brief because a flyby never stops. Voyager approached, crossed the system, and continued toward Neptune. Uranus did not pause its seasons so the spacecraft could watch a complete cycle. That single fact shapes almost everything we think we know about the planet. Voyager found a world that looked almost featureless in the visible images available at the time. It measured a magnetic field, tipped sharply away from the rotation axis and offset from the planet's center. It discovered new moons and rings. It saw a system arranged around a planet lying on its side. And its energy measurements supported the idea that Uranus released very little internal heat. There was nothing careless about that conclusion. It was the best interpretation available from an unprecedented encounter. The problem was not that Voyager saw too little to matter. The problem was that it saw one chapter of a very long book. Uranus takes 84 Earth years to go around the Sun. Since the 1086 flyby, the planet has not yet completed one full orbit. Its extreme tilt gives it seasons unlike those of the other giant planets. A region illuminated for years can later move into years of darkness. Clouds and haze respond. The visible brightness of the disk changes. Thermal conditions in the atmosphere may lag the sunlight that drives them. To build a true orbital average energy budget, Researchers had to connect observations taken from different telescopes, at different wavelengths, under different viewing geometries, then model how the missing portions fit together. That is not a replacement for Voyager. It is what became possible because Voyager established the close baseline and later observatories extended the timeline. The risk of a single encounter became especially clear in another part of Uranus science. Decades after the flyby, researchers returned to Voyager's magnetic and plasma data and found evidence that the solar wind had compressed the magnetosphere shortly before the spacecraft arrived. The conditions may occur only about 4% of the time. For years, features seen during that encounter helped define the textbook Uranian magnetosphere. The reanalysis suggested Voyager may have arrived during unusual space weather. That does not mean the magnetic measurements were wrong. It means a real measurement can capture an unusual state. The heat budget correction is not the same result and should not be confused with it. Solar wind compression did not manufacture the new internal heat flux. The magnetosphere story is valuable because it teaches the same discipline. One close look can be both priceless and incomplete. Voyager gave us the only direct encounter with Uranus. Earth-based telescopes, Hubble, infrared observatories, and now modern reanalyses give us duration. The mystery changes when the snapshot and the timeline are allowed to speak together. There is also a human-scale trap in the phrase, almost 40 years. It sounds like a long time. It is a long time for a career, a spacecraft program, or a generation of researchers. At Uranus, it is less than half a year. The planet has moved from the geometry of the flyby through equinox and onward, while astronomers watched changing clouds and polar structures emerge. The apparently bland world became active. The old visual portrait softened before the heat ledger was formally revised. None of this diminishes Voyager 2. It reveals what a flyby is. A flyby is an incision through time. It can expose layers no telescope can reach, and still leave the temporal anatomy unknown. Once that limit is accepted, the 2025 analyses make sense as the next stage, rather than a correction issued from nowhere. They did not discover a new furnace switching on. They recovered a weak but persistent surplus that becomes visible only when the accounting stretches wide enough. Now we can compare the two modern Uranus budgets more carefully. The first important point is agreement on sign. Both say the outgoing energy is greater than the absorbed sunlight. Uranus has an internal contribution. The second point is scale. The contribution is small compared with the total thermal radiation emitted by the planet. Most of that outgoing radiation ultimately replaces absorbed sunlight. The internal part is the remainder. The third point is uncertainty. An internal flux of 0.078 watts per square meter, with an uncertainty of 0.018, is not a point etched into stone. It is a range informed by data and model choices. Even near the high end of that range, Neptune remains far more luminous from within. The fourth point is season. A planet can temporarily absorb more or less energy than it emits without violating physics. Oceans and atmospheres on Earth store and release heat across seasons. A giant planet can do the same through its atmosphere and deeper layers. The scientific target is not a momentary mismatch. It is the orbitally averaged flow that remains after seasonal storage is accounted for. This is why the older debate included a difficult possibility. What if Uranus only appeared to have a near-zero internal flux because it was observed at an unrepresentative season? The new work reduces that escape route. The low flux seems to represent the planetary average rather than a brief seasonal accident. Season still matters because the planet is tilted into one of the most extreme lighting geometries in the solar system. At solstice, sunlight favors one polar hemisphere for years. Half an orbit later, the relationship reverses. Near equinox, the sun passes over the equatorial region. The absorbed power changes with latitude long before deep material can respond. The atmosphere can store part of that imbalance. Haze can brighten or darken. Clouds can alter reflectivity. Winds can carry energy across latitude. Infrared radiation can lag the changing sunlight. When researchers combine observations from different years, they have to distinguish this seasonal breathing from a persistent internal surplus. Imagine checking a building's energy use at noon in summer and again at midnight in winter, then trying to infer the heat leaking from its basement. The local readings are real, but the building's thermal mass and weather response stand between a snapshot and the annual average. Uranus adds another complication. We view the planet from a changing angle as both Earth and Uranus move. A bright polar cap contributes differently to the observed disk when the pole faces us than when the equator does. Instruments cover different wavelengths and have different calibration histories. Some observations resolve latitude. Others record an integrated point or disk. The modern analyses address these problems with radiative transfer models and long observational baselines. A model estimates how radiation interacts with gases and aerosols, then fills gaps between measured wavelengths and viewing geometries. The output is checked against the available data. That use of a model does not make the result imaginary. Every global planetary budget includes inference because no instrument can surround a planet with a perfect sphere of detectors for 84 years. The standard is whether the assumptions are explicit, the uncertainties propagate, and independent approaches converge. They now converge on a positive internal flux. Future observations can still improve the value. Better reflected light spectra can refine the bond albedo, the fraction of all incoming sunlight reflected across all wavelengths and directions. Better thermal spectra can refine the outgoing infrared flux. Longer coverage can reveal whether the global average drifts with season more than current models expect. If the central estimate moves from 0.078 to a nearby value, the conclusion may remain intact. Uranus has a small positive internal heat flow. Neptune's is several times larger. This is another mark of a durable scientific statement. It does not depend on worshipping one exact decimal. It survives reasonable revision. Low does not mean impossible. That is the fifth and most important point. For years, Uranus's faint internal output was described as a puzzle in itself. Some simple cooling models did struggle with it, but if a planet begins with a plausible amount of energy and loses it over billions of years, An internal flux near the new Uranus value need not violate an ordinary cooling history. In a 2026 analysis, David Stevenson stated the reversal plainly. The low Uranus heat flow is not necessarily the puzzle. The difference with Neptune is that change in emphasis is scientifically healthy. A mystery should not survive merely because it is famous. It should survive because the latest evidence still forces an explanation. The latest evidence forces a comparison. Take the best current values and return to our square meter frames. Over Uranus, the internal contribution is near 0.08 watts. Over Neptune, it is near 0.4. The ratio is about 5. Now multiply across each world. Neptune is slightly smaller in radius than Uranus, so its total surface area is also slightly smaller. Yet every comparable patch, on average, is carrying outward much more internal power. The global contrast remains enormous. The word internal includes several possible reservoirs. There is heat retained from formation. There is energy released as material changes density or separates. There may be energy associated with phase changes deep inside. Radioactive decay in rocky material contributes over time. The measured flux does not label which source supplied each joule. What it does reveal is the rate at which the present planet is losing stored energy to space. Neptune is draining faster. This is where appearance becomes deceptive. Uranus and Neptune are both blue because methane in their atmospheres absorbs red light. Both have hydrogen and helium envelopes enriched in heavier material compared with Jupiter and Saturn. Their radii are close. Their masses belong to the same broad planetary neighborhood. Textbooks place them side by side. If that visible family resemblance extended all the way down, their heat flows would not have to match perfectly. Planets are individuals, but a factor near 5 is large enough to demand a reason. There are only a few broad possibilities. The two planets could have started with different internal energy. They could contain different proportions or arrangements of rock, volatile material, hydrogen, and helium. Heat could move through one interior more efficiently than the other. Their atmospheres could impose different bottlenecks. Major impacts could have changed mixing or stripped material, or their evolution could combine several of these routes. Notice what is not on that list. The explanation is not simply that Uranus is farther from the Sun. It is not. Neptune is farther away, yet it emits more internal heat. The explanation is not simply that Uranus is colder at its cloud tops. Temperature at one atmospheric level is not the same thing as the total internal energy stored below. The explanation is not simply that Neptune has stronger winds. Those winds are part of the outcome, and perhaps part of the energy transport, not a label that closes the causal chain. Neptune receives less sunlight, but its atmosphere remains extraordinarily active. Its internal energy helps drive convection, clouds, and storms. It emits more than twice the energy it absorbs from the Sun. Uranus emits only modestly more than it absorbs. Place the planets in a dark room with the Sun removed as a thought experiment. Both would continue glowing in infrared because both have internal energy. Neptune would be brighter from within. The thought experiment is useful but incomplete. The real planets do receive sunlight. Their atmospheres blend solar and internal energy. Cloud patterns respond to rotation, chemistry, seasonal illumination, and flows that reach far below the visible tops. We cannot point to a storm and assign each motion to one energy source. Still, the global ledger imposes a boundary. Whatever story we tell about the interiors must allow Neptune to deliver roughly 5 times more heat through its atmosphere today. That makes Neptune a control case of a peculiar kind. It is not a controlled laboratory twin. It is the nearest available planet with similar bulk properties. Differences that once looked like a list of oddities now become clues within a single comparison. Uranus lies on its side. Neptune does not. Uranus has an extremely tilted and offset magnetic field. Neptune's field is also unusual, but its geometry is not identical. Uranus has a colder upper atmosphere minimum. Neptune drives more visibly active weather. Their satellite systems differ. Their present orbits differ. Their histories may have included different collisions and migration paths. The planets are similar enough to make the contrast meaningful, and different enough to keep it unresolved. That is why Neptune is the real mystery. Not because Neptune behaves impossibly, but because every successful explanation of Uranus must also explain why the neighboring member of its supposed class took another route. The problem has changed from a single cold world to a broken symmetry. Broken symmetries are powerful in science. When two systems that appear similar behave differently, the difference can reveal a hidden variable. Here, the hidden variable may be composition, structure, history, or transport. To find it, we have to stop treating ice giant as an answer. The phrase sounds as though it describes a known interior. It does not. Uranus and Neptune earned the label because they differ from Jupiter and Saturn. The two outer planets contain a larger share of elements heavier than hydrogen and helium. In planetary science, water, methane, and ammonia are often grouped as ices because they condensed as solids in the cold region where giant planets formed. Deep inside a modern planet, those materials would not resemble ice from a freezer. Pressure and temperature can force them into dense fluids, ionic phases, or other states that are difficult to reproduce and measure. So an ice giant is not necessarily a giant ball of familiar ice. It is a category built from formation chemistry and bulk composition, useful, but broader than the picture it creates in the mind. Even the visible similarities are less exact than they first appear. Uranus has about 14.5 times Earth's mass. Neptune has about 17.1. Uranus is slightly larger in equatorial diameter, while Neptune is denser. Their rotation periods are not known with the same certainty we have for a solid planet, because the visible atmospheres move and the magnetic fields provide imperfect clocks. Their blue colors are related to methane, but haze and deeper cloud structure also shape the precise shade. Then the major differences begin. Uranus's axis is tilted by about 98 degrees. Rather than spinning like a top that is mostly upright relative to its orbit, it rolls around the sun. At solstice, one pole points broadly toward the sun, while the other faces away. Near equinox, sunlight falls more directly across the equatorial region. The pattern changes over decades. Neptune's axial tilt is much closer to Earth's, though its seasons still last for many years because its orbit is so long. Uranus's magnetic field is tilted by roughly 60 degrees from the rotation axis and displaced from the planet's center by about 1/3 of a radius. As the planet rotates, that geometry produces a wildly varying magnetosphere. Neptune's field is also tilted and offset, a clue that both dynamos may operate in shells rather than compact metallic cores. But the exact structures and environments differ. Uranus can reach minimum temperatures near 49 kelvins in the upper atmosphere, making parts of it colder than corresponding levels at more distant Neptune. Yet cloud tracking has found Uranian winds reaching around 900 kilometers per hour. A weak internal heat flux does not produce a dead atmosphere. Neptune can drive winds faster still. Its dark storms appear, drift, and disappear. Bright methane ice clouds trace rapid flow. Its greater internal heat likely helps sustain this activity, but sunlight, rotation, and atmospheric structure also matter. The planet's moons and rings provide another contrast. Uranus has a tightly arranged system aligned with its tilted equator, as though the entire local architecture shares the planet's sideways orientation. Neptune has Triton, a large moon moving backward relative to the planet's rotation, almost certainly captured from the outer solar system. That capture may have destroyed or reorganized an earlier satellite system. If histories can reshape moons so profoundly, it should not surprise us that they can reshape interiors. This list is not included to make Uranus sound strange. Strange is not an explanation. The list has a stricter purpose. It tells us that the word twin describes a controlled comparison only at the broadest level. Uranus and Neptune are close enough in mass and radius that a shared category is justified. They are different enough that the category cannot predict their heat flow by itself. In fact, the heat difference may be the clearest warning against assuming too much from size. Astronomers often begin with quantities that can be measured from far away. A planet's mass can be inferred from its gravitational pull on moons or a host star. Its radius can be inferred from imaging or the amount of starlight it blocks during a transit. Average density follows from mass and volume. Those measurements are powerful. They are also radically incomplete. Imagine 3 sealed spheres with the same mass and diameter. One contains a dense core beneath a light envelope. Another contains material mixed gradually, from center to atmosphere. A third has several stable layers that resist mixing. From outside, the balance and ruler give the same answer. Their cooling histories do not. This is the problem with Uranus and Neptune. We are trying to reconstruct deep structure from effects at the surface. The planet is an inverse problem. In a forward problem, we choose an interior and calculate its gravity, radius, magnetic field, and heat. In the inverse problem, we measure gravity, radius, magnetic field, and heat, then ask which interiors could have produced them. More than one can. Modern models can build water-rich Uranus interiors that match the observed mass and radius. They can also build rock-rich versions, They can distribute heavy material in distinct shells or in gradual composition gradients. They can assume most of the deep interior convex efficiently, or that large regions remain stably stratified. The term rock-rich does not mean a dry, solid planet beneath the clouds. At the pressures inside Uranus, rock, water, hydrogen, and other materials may interact, dissolve, separate, or form phases that have no simple surface equivalent. The point is not to replace ice giant with rock giant. It is that both labels outrun the evidence if treated literally. A 2025 interior study demonstrated this degeneracy directly. With current constraints, models dominated by water and models containing far more rock can both remain viable. Some of those models place electrically conducting ionic water in regions capable of generating the magnetic field. Others change the location and depth of the dynamo. That means the unusual magnetic geometry is not a decorative oddity. It may help discriminate among interiors, but it cannot do so alone, because different distributions of conducting material can produce complicated fields, and our best close magnetic data came from a single flyby under unusual solar wind conditions. Gravity has the same double nature. A planet's gravity field reveals how mass is distributed and how the world responds to rotation. Precise measurements of gravitational harmonics can distinguish a centrally concentrated planet from one with heavy material distributed farther outward, yet clouds, winds, uncertain rotation, and limited spacecraft tracking can complicate the inference. Heat adds a new constraint. A model that matches mass and radius but cools far too quickly or far too slowly is incomplete. A model that matches Uranus but would force Neptune into the same low flux has failed the comparison. This is why the new energy budget matters beyond 0.078 watts. It tightens the inverse problem. The old near-zero value encouraged models that needed to suppress almost all outward internal heat. The new value allows a wider range of ordinary cooling paths for Uranus. At first glance, that sounds like a loss of information. If more models can fit, have we learned less? No. The corrected measurement removes a false target. We no longer need a mechanism extreme enough to make the flux vanish. We need a mechanism that produces a low positive flux at Uranus, while allowing a much larger one at Neptune. That comparative requirement is more physical. It asks for a history rather than a trick. To see why history matters, follow a parcel of energy from formation to space. When a young planet gathers material, gravity accelerates that material inward. A collision converts some of the motion into heat. As the growing planet compresses, its interior becomes hotter. Dense components tend to sink, while lighter components rise, releasing additional gravitational energy. The planet begins its life swollen and energetic. It then cools and contracts. Contraction deserves emphasis, because a giant planet does not behave like a hot stone that only loses stored warmth. As it radiates energy, gravity can pull the planet into a slightly more compact state. That contraction releases more gravitational energy. The temperature at some depths can even rise, while the planet as a whole loses energy. This is one reason internal luminosity cannot be read as a simple remaining percentage of a starting battery. The energy reservoirs exchange with one another. Thermal energy, gravitational energy, phase changes, and differentiation contribute under different conditions. The rate seen at the top of the atmosphere depends on the slowest relevant transport process below. Material physics becomes decisive. At shallow pressure, hydrogen behaves as a molecular gas. Deeper down, it becomes a dense fluid. Water, methane, ammonia, silicates, and iron enter regimes where familiar names hide unfamiliar states. Molecules can dissociate, ions can move, components can mix at one pressure and separate at another. Electrically conducting regions can support a dynamo. Laboratory experiments can squeeze small samples with diamond anvils, or launch shock waves through them. Quantum calculations estimate how materials behave where experiments are difficult. The result is an equation of state, a relationship among pressure, temperature, density, and composition. Every interior model depends on these relationships. If the equation of state says a mixture is denser at a given pressure than previously thought, the amount of rock or volatile material needed to match the planet's mass changes. If components dissolve into one another, a sharp core boundary may blur. If a phase transition absorbs or releases energy, the cooling curve changes. If electrical conductivity rises in a particular region, the plausible dynamo location moves. Uncertainty in material physics therefore becomes uncertainty in planetary biography. This is not an excuse that allows any model to survive. Experiments, calculations, and multiple planetary constraints limit the range. It is the reason two respectable models can start from the same measured radius and arrive at different interiors. The cooling rate also responds to the atmosphere as a boundary condition. The deep interior may be opaque, but the planet finally loses energy from levels where infrared radiation can escape. Clouds and absorbing gases determine how the temperature at those levels relates to the entropy below. Change the atmospheric composition, and the same interior can cool at a different rate. Young planets are especially sensitive because they begin hotter and larger. A change in the assumed starting state can persist for a long time if cooling is slow. Modelers sometimes describe a hot start or cold start, not as literal single temperatures, but as families of initial energy states shaped by formation. For a planet 4.5 billion years old, some memory of the initial condition may fade. A strong transport barrier can preserve it. This gives the Uranus-Neptune ratio several possible origins that look identical in the final arithmetic. Uranus might have started with less accessible internal energy. It might have lost energy more rapidly early on, then become faint. It might still contain considerable heat beneath a barrier. Neptune might have started hotter, remained better mixed, or experienced later events that changed its cooling. The measured flux alone cannot separate initial inventory from transport efficiency. Age does not separate them either, because the planets are the same age, only in the broad solar system sense. Their assembly could have ended at different times. A few million years is tiny, beside 4.5 billion years, but it can be decisive while the gas disk exists and giant planets acquire envelopes. This is why a successful model is run forward. Researchers choose a formation state, composition profile, material equation of state, atmospheric boundary, and transport prescription. They calculate how radius, luminosity, and structure change with time. At the solar system's present age, the model must match the measured planet. Matching only today's luminosity is easy enough to be misleading. The same model must also reach the right radius, mass distribution, atmospheric composition, and magnetic possibilities. Neptune must be modeled with equal care. If one set of assumptions fits Uranus only by making Neptune impossible, it has not explained the pair. If separate assumptions fit each planet but have no plausible formation route, the exercise has described outcomes without explaining origins. The factor near 5 is therefore not merely a ratio to place in a title. It is a boundary condition on two calculations that have to begin in the same young solar system and end at two different worlds. This deeper view also repairs the image of trapped heat. Heat is not a glowing liquid waiting behind a solid lid. The interior may have gradual gradients, convecting layers, conductive interfaces, and phase boundaries. Energy is distributed through material whose density and state change continuously with depth. A transport barrier is a property of that structure, not a physical ceiling suspended over a furnace. That matters visually and scientifically. A literal fiery core beneath an icy shell would make a strong picture and a weak claim. The honest picture is less familiar. It is a set of possible density and composition profiles, each capable of producing the same exterior until another measurement distinguishes them. Now we are ready for the most famous proposed history, because we know what it has to change. The most famous proposed history begins with a collision. Long before Voyager, Uranus's sideways rotation demanded an origin story. A planet does not normally form with its spin axis lying almost in its orbital plane. In a disk of gas and solids, orbiting a young sun, angular momentum tends to create more orderly rotation. Something likely disturbed Uranus. A giant impact is an obvious candidate. During planetary formation, growing worlds collided. An object perhaps comparable to Earth in scale could have struck young Uranus, transferring angular momentum and tipping the planet. That sentence appears in almost every popular account. It is plausible. It is not complete. An impact is not one event with one outcome. Change the impactor's mass, speed, composition, angle, or the state of Uranus at the time, and the result changes. A direct collision can drive material deep. A grazing collision can transfer angular momentum while leaving more of the envelope intact. Debris can escape, fall back, or form a disk from which moons emerge. Energy can be deposited in the outer envelope or carried into deeper regions. Those details matter for heat. One simple story says the impact tipped Uranus and somehow trapped its internal energy. But an impact adds energy. If it mixes the planet thoroughly, it may make the interior more uniform and help heat escape. If it strips part of the envelope, it changes pressure and composition. If it creates a stable gradient with heavier material beneath lighter material, it may suppress later convection. The same broad cause can point toward different thermal outcomes. That is why tilt alone cannot prove the heat mechanism. A successful impact model must do several jobs at once. It must reproduce the planet's spin orientation and angular momentum. It must leave a plausible mass and composition. It must account for the equatorial ring and moon system, or at least avoid destroying the conditions needed to form it. It must create an interior whose gravity and magnetic field are compatible with what we measure. Then, it must cool for billions of years and arrive near today's heat flux. This is a much harder standard than producing a sideways planet in one simulation frame. Some simulations find that a grazing impact can tilt Uranus while placing debris into orbit, providing material from which moons might form. Others explore multiple smaller impacts rather than one enormous collision. Some thermal models use an impact to establish a composition gradient that later acts as a barrier to convection. None has become a single accepted biography. The moons make the problem especially interesting. Uranus's large classical moons orbit close to the planet's equatorial plane, which is itself tilted. Their orderly motion suggests they formed from or settled into a disk linked to Uranus after the tilt was established. But matching the moon's combined mass, composition, and orbital spacing constrains the debris available after an impact. The planet cannot be modeled in isolation from its system. Neptune deepens the comparison again. It may also have experienced giant impacts. The capture of Triton certainly transformed its satellite system and may have altered the planet's later environment. Yet Neptune did not end with Uranus's axial tilt, and it did not end with Uranus's low heat flux. So even if a giant impact is part of the answer, the useful question is not, did Uranus get hit? The useful question is, what impact history could leave all the evidence we see and produce a thermal evolution different from Neptune's? At present, the answer is a set of competing possibilities. That uncertainty is not a failure of imagination. It is a consequence of having too few deep measurements. There is another way to explain a low outward flux that does not require the interior to be cold. It only requires the interior to be bad at moving heat. To see it, think of a pot of water warming on a stove. As water at the bottom heats, it expands and becomes less dense. Buoyancy carries it upward. Cooler, denser water sinks. The circulating motion transports energy much faster than molecular conduction alone. This is convection. Giant planet interiors can also convect, though the materials, pressures, and timescales are vastly different. If a deep region is nearly uniform in composition and the temperature gradient is steep enough, warm material can rise and cooler material can sink. Energy moves outward through large-scale motion. Now dissolve more heavy material in the bottom of the pot and less near the top. Heating still tries to make the lower material rise, but the composition difference makes it denser. If the stabilizing composition gradient is strong enough, it can resist overturning. The planet becomes layered. Heat can still cross the stable region by conduction, radiation in some conditions, small-scale layered convection, or slow mixing. It crosses more slowly than it would through a fully convecting interior. This distinction creates one of the most important repairs to the popular Uranus story. Low outgoing heat does not necessarily mean little heat remains inside. Uranus could be relatively hot at depth and still appear faint if a stable region throttles the flux. Thermal evolution models have shown that composition gradients, or a deep thermal boundary, can reproduce a low present luminosity under certain assumptions. In some versions, the outer envelope cools, while a deeper region keeps much of its energy for billions of years. The planet would resemble a house with a warm room behind an insulated wall. A thermometer outside the wall measures little escaping heat. It does not reveal the temperature of the hidden room without a model of the insulation. This is an attractive explanation because it connects formation to present heat. Heavy material deposited unevenly during accretion, differentiation, or an impact could establish the gradient. The gradient then survives, at least partly, and alters cooling over the age of the solar system. It can also connect to magnetism. If convection occurs mainly in a shell of electrically conducting material above or around a stable deep region, the dynamo may produce a field that is strongly non-dipolar, tilted, and offset. Uranus and Neptune both have unusual fields, which is one reason shell dynamos are studied. But attractive is not the same as confirmed. The stable layer is not an object Voyager photographed. It is a structure inferred because it helps models match certain observations. Its properties are uncertain. Where does it begin? How thick is it? Is the composition change sharp or gradual? Does layered convection carry more heat than a simple conductive barrier? Can the gradient survive mixing for 4.5 billion years? Does it yield the measured gravitational harmonics and magnetic geometry? Change those assumptions, and the cooling curve changes. A barrier strong enough to suppress heat may also alter how the planet contracts. That affects radius. It may change where electrically conducting phases occur. That affects the magnetic field. It may preserve a hot, deep interior whose density distribution affects gravity. The explanation has consequences, which means it can be tested. This is the moment when the Uranus-Neptune comparison becomes especially strict. If both planets formed with composition gradients, why did one retain a stronger barrier? If only Uranus did, what event created it? If Neptune is more thoroughly mixed, what prevented the same mixing at Uranus? If impacts are responsible, why did their impact histories diverge in the required way? The barrier does not end the story. It relocates the question into the planet's early histories. There is also a possibility between fully mixed and fully stable. A planet may contain many thin convective layers separated by composition interfaces. Heat moves within each layer, then crosses the boundary to the next. Over long times, layers can merge or persist. The effective heat transport lies between efficient whole-region convection and slow conduction. Small differences in initial composition or layer structure can then grow into large differences in present luminosity. This sensitivity is both promising and dangerous. It offers a route to the factor of 5. It also means a model can be tuned unless independent observations constrain the layers. That is why heat cannot be interpreted alone. The new flux tells us how much energy reaches space. Gravity tells us where mass is concentrated. Magnetism tells us where conductive material is moving. Atmospheric composition tells us what ingredients the planet acquired. Moons and rings record aspects of the system's dynamical history. An interior model earns credibility when it explains several of these at once. At present, layered cooling is a serious contender. It is not a hidden fact waiting to be narrated as certainty. The most honest version is conditional. If Uranus contains a strong, stable region that Neptune lacks, the planet may still hold deep heat while releasing little of it. If future gravity, magnetic, and atmospheric data point toward a more thoroughly mixed Uranus, that explanation will weaken. The distinction matters because the same visible flux can describe two very different worlds. One is genuinely cool throughout after losing much of its original energy. The other is thermally divided, with an old reservoir still waiting below. From Earth, both can look equally faint. How could we tell them apart? Start with gravity. As a spacecraft orbits a planet, tiny changes in speed reveal variations in the gravitational field. A world with most of its heavy material packed tightly toward the center pulls differently from one with heavy elements distributed through a broad interior. Rotation deforms the planet, producing a series of measurable harmonics. Winds can also shift mass and contribute to the signal. For Uranus, the existing gravity coefficients are limited by the geometry and duration of the Voyager flyby. They constrain models, but not enough to choose one architecture. A dedicated orbiter passing over many latitudes and distances could improve the field and separate static interior structure from atmospheric motion. A stable, deep layer should affect the density profile. It may place a composition transition at a particular depth. Different transitions can yield different gravitational signatures. The connection is not one-to-one, but better gravity makes the family of acceptable interiors smaller. Now consider the magnetic field. A planetary dynamo needs electrically conducting material in motion. In Earth, that motion occurs in a liquid iron outer core. In Uranus and Neptune, models often place the dynamo in a shell where water, ammonia, methane products, or mixtures become conductive under high pressure. A shallow shell can produce complex fields with large non-dipole components. If a stable region confines convection to a particular shell, the magnetic geometry should carry information about that confinement. Repeated mapping could reveal which field components are internal and stable, which are induced by interactions with the solar wind, and how the magnetosphere changes as the tilted field rotates. Voyager gave a first cut. It could not provide a full magnetic movie. Atmospheric composition provides a third test. The abundances of noble gases, methane, hydrogen compounds, and isotopes can preserve information about formation temperature and location. Some species are difficult to measure remotely because clouds and opacity hide the deeper atmosphere. An entry probe could descend below the visible layers and sample them directly. Those abundances would not print the planet's birthplace on a display. They would restrict which building materials were available and how they were incorporated. Then there is the heat map itself. The current global value is an average. A barrier model can predict how internal heat should vary with latitude and time. especially on a planet with extreme seasonal illumination. If the deep flux is nearly uniform, while the upper atmosphere stores and releases solar energy, one pattern emerges. If internal transport is channeled or connected to large-scale circulation, another may emerge. Repeated infrared measurements across years would begin to separate those patterns. Finally, the moons can act as witnesses. Their orbits and compositions record the debris and dynamical environment around Uranus. Evidence of internal oceans or geological activity within the moons would reveal how tidal and radiogenic heat operated in the system. Their masses and moments of inertia, if measured accurately, would constrain what material formed the satellite disk. None of these tests can be treated as an isolated verdict. Suppose improved gravity favors a strong composition gradient, but magnetic mapping suggests a deep dynamo, inconsistent with the same model. The model must change. Suppose atmospheric abundances indicate a formation path that should have produced efficient mixing, but the heat remains low. An impact or later differentiation may become more important. Suppose moon compositions conflict with debris expected from a giant grazing collision. The impact geometry narrows. This is how competing explanations become science rather than a menu of possibilities. They are forced to share the same evidence. At the moment, the evidence matrix contains many blank cells. That is why no single model has won. It is also why a Uranus mission would have unusual leverage. The instruments would not answer separate trivia questions. They would interrogate one connected history. Before we build that mission in detail, there is another possible bottleneck above the deep interior. Heat that reaches the atmosphere still has to cross it. The visible atmosphere of Uranus is mostly hydrogen and helium, with methane and other trace species. Deeper down, temperature and pressure rise. Materials that are vapor at one level can condense at another. Condensation releases latent heat. It also changes the composition and density of moving parcels. On Earth, water vapor condenses into clouds and helps power storms. In a hydrogen-rich giant planet, condensation of heavier species can have a counterintuitive effect. Remove a heavy vapor from a rising parcel, and the remaining gas becomes lighter, which can encourage motion. But gradients in mean molecular weight can also inhibit convection. The exact result depends on composition, phase behavior, and the vertical temperature profile. Some models have asked whether condensation of methane or water could slow cooling enough to explain Uranus. The mechanism is physically real. The question is magnitude. One calculation found that condensation effects could alter cooling by around 15% under its assumptions. Significant enough to matter, but not enough by itself to turn the Uranus value into Neptune's or the reverse. Different equations of state and atmospheric structures can shift the result. So this is not a universal ceiling. It is a warning against making the atmosphere a single complete answer. The atmosphere may be a gate. The current evidence does not show that it is the whole wall. This distinction helps explain why visible weather can mislead. Uranus looked bland to Voyager's cameras, but later observations found clouds, storms, and changing polar haze. Cloud-tracked winds can reach about 900 kilometers per hour. a planet with low internal heat can still have organized motion because sunlight, rotation, vertical shear, and atmospheric waves continue to operate. Neptune's greater internal heat gives its atmosphere another energy source, and its storms are often more conspicuous. Yet no formula says 5 times the internal heat produces 5 times the wind speed. Jet formation depends on how energy is converted into motion, how eddies transfer momentum, how deep the winds extend, and how friction or magnetic drag removes energy. Weather is evidence of transport. It is not a direct thermometer for the center. The coldest measured levels create a similar trap. Uranus can reach around 49 kelvins in its upper atmosphere, colder than Neptune at comparable levels despite being closer to the Sun. That fact is striking, but it does not mean the entire Uranian interior is colder than Neptune's. Temperature is local. Heat content is distributed. Heat flux is a rate. A thin, high layer can be extremely cold, while a deep reservoir remains hot. A planet can have a warm interior and a low outward flux if transport is slow. Another planet can have less total stored energy at some depth, yet release it faster at the surface. Without an interior model, the cloud top temperature cannot settle the comparison. This is why the phrase Uranus is the coldest planet is risky. It compresses a vertical atmosphere and an unknown interior into one adjective. The better statement is precise. Uranus reaches exceptionally low temperatures in parts of its upper atmosphere. Its globally averaged internal heat flux is positive and low. Its deep temperature profile is model dependent. Precision here does not make the story smaller. It creates room for the actual mystery. If neither one giant impact, one stable layer, nor one atmospheric mechanism can claim the result alone, we have to move backward toward formation. Uranus and Neptune did not begin as finished blue spheres placed into their current orbits. They grew within a disk of gas, dust, and larger bodies around the young sun. The outer disk contained volatile-rich solids, but forming planets with 15 to 17 Earth masses before the gas disappeared is not easy in every model. Growth rate depends on the supply of solids, the motion of pebbles and planetesimals, interactions with gas, and the planet's migration through the disk. The order of events matters. If one planet built a core early, it could capture a hydrogen-helium envelope while the disk was dense. If another assembled later or in a region with a different supply of solids, its envelope and heavy element distribution could differ. Rapid pebble accretion might create a gradual composition gradient instead of a clean core. Giant impacts late in formation could mix or stratify what had already accumulated. The final masses can converge even when the paths do not. This is familiar in a simpler setting. Two houses can have the same exterior dimensions and total mass. One was built around a steel frame with open rooms. The other contains thick interior walls and isolated chambers. An outside scale and tape measure cannot recover the construction sequence. The way heat moves through the houses can. For planets, today's heat flux is one clue to the construction sequence. Migration complicates the scene. Models of the early solar system allow the giant planets to move from their formation locations as they exchanged angular momentum with gas and smaller bodies. Uranus and Neptune may not have formed exactly where they orbit now. In some dynamical histories, they can even exchange order during an unstable period. That does not mean a specific swap is established. It means present distance from the Sun is not a complete record of formation temperature or material supply. Neptune may have acquired a different ratio of rock, volatile material, hydrogen, and helium. It may have formed a weaker stabilizing gradient. It may have experienced impacts that mixed the interior rather than isolating it. It may simply have retained a more efficient path for convection. Uranus may have done the opposite. Once again, several differences can act together. A collision can create a composition gradient. A gradient can alter the dynamo. The altered heat transport can change atmospheric evolution. The Moon system can preserve debris from the collision. Formation is not one explanation competing with impact and layering. It is the stage on which those processes connect. That is why the phrase "twins that diverged" is useful only if we are careful. The planets may have diverged after similar beginnings. They may also have arrived at similar sizes through different beginnings. Were they ever twins? We do not know. But the heat flow gives a criterion that any biography must meet. It must produce two present worlds with similar bulk scale and a roughly 5-fold difference in outward internal energy. We can now place the main explanations in a shared matrix. Begin with the giant impact route. Its strongest evidence is Uranus's extreme tilt and the aligned satellite system. Its challenge is uniqueness. Many impact geometries can tip a planet, and their thermal consequences differ. The route gains strength if detailed simulations reproduce the spin, satellite material, interior gradient, gravity field, and present flux together. It weakens if those requirements conflict. Next, the stable interior route. Its strongest feature is mechanism. A composition gradient can directly reduce heat transport while preserving deep energy. It may help create a shell dynamo and a complex magnetic field. Its challenge is direct evidence. We do not yet know the gradient's location, strength, or longevity. The route gains strength if precision gravity and magnetic data require a stratified interior. It weakens if a fully convective model fits the same data and thermal history. Then, atmospheric throttling. Its strongest feature is that condensation and composition unquestionably affect convection. Its challenge is magnitude. Current models do not clearly produce the entire Uranus-Neptune disparity from atmospheric physics alone. The route gains strength if observed temperature, composition, and heat patterns match a persistent atmospheric bottleneck. It weakens if the necessary inhibition exceeds plausible chemistry. Finally, different formation and accretion histories. This route is broad enough to contain the others, which is both a strength and a weakness. Different births can explain different composition gradients and impact histories. But a broad story can fit anything unless it predicts measurable abundances, structures, and system architectures. The route gains strength when a specific formation model produces the observed atmosphere, gravity, moons, spin, magnetic field, and thermal evolution. It weakens when the history is invoked only after the fact. The matrix reveals something important. No explanation is waiting for one heat measurement to declare victory. The measurements are coupled. An atmospheric probe could test formation chemistry. An orbiter could test gravity and magnetism. Repeated infrared mapping could test heat transport. Moon flybys could test the impact and disk history. Long-time coverage could separate seasonal change from deep output. This is the causal chain of the episode. The corrected heat ledger changes the mystery. The new mystery forces a comparison. The comparison exposes multiple interiors. Multiple interiors require cross-checks. The cross-checks define a mission. Before that mission, scientists will continue to improve the case from Earth and existing space telescopes. Uranus is no longer the bland disk Voyager saw in visible light. Modern images reveal bright clouds, polar caps, rings, and seasonal change. Infrared spectra constrain temperatures and gases. Stellar occultations probe atmospheric structure and rings. Laboratory experiments and quantum calculations improve the equations of state used deep inside. Each advance shrinks part of the uncertainty. But some ambiguities are geometric. A telescope sees the planet from outside. It can measure radiation escaping from levels where the atmosphere becomes transparent. It cannot directly sample well-mixed gases below opaque clouds. It cannot orbit for years to map the gravity field through changing trajectories. It cannot fly through the magnetosphere from every local time. That is why proximity still matters. The magnetic field offers a perfect example of both promise and limitation. On Earth, a compass points approximately north because the field near the surface is dominated by a dipole aligned fairly close to the rotation axis. Uranus is different. Its magnetic axis is tilted by roughly 60 degrees, and the effective center of the field is displaced by about 1/3 of the planet's radius. As Uranus rotates, the field presents a changing orientation to the solar wind. The magnetotail can twist into a corkscrew-like structure. Charged particles move through a system whose geometry changes on the planet's rotation period. This complexity is often used as evidence for a dynamo operating in a relatively shallow shell. A thin, convecting shell can produce stronger, high-order field components at the surface than a deep, compact dynamo. If the interior is layered, the conducting region may occupy just such a shell. That connection is plausible. It is not unique. The field measured outside a planet combines internal generation with currents in the magnetosphere. Solar wind pressure changes the external system. Voyager crossed one trajectory at one time. The 2024 reanalysis of that encounter suggests the magnetosphere was unusually compressed. So the magnetic clue arrives with a warning label. It may carry information about deep structure, but the environmental contribution must be separated first. An orbiter could repeat measurements across many rotations, seasons, solar wind conditions, latitudes, and distances. Stable components would emerge from the changing external field. The internal magnetic map could then be compared with dynamo models tied to particular interior layers. The same spacecraft's radio signal could track tiny accelerations caused by gravity. Heat instruments could map outgoing infrared radiation. A probe could measure atmospheric gases. These observations would not sit in separate chapters after the mission. They would constrain the same models at the same epoch. Suppose magnetic mapping favors a shallow conducting shell. Gravity favors a broad, heavy element gradient. Low heat favors inhibited convection. Together, the stable layer case becomes stronger. Suppose instead, the magnetic field can be produced in a deeper, more mixed region. Gravity allows efficient convection, and atmospheric measurements show a formation composition unlike Neptune's. The story shifts. The important point is not which example sounds more persuasive now. The important point is that the unknown has become conditional. We know what kinds of observations would make the alternatives move. The atmosphere needs the same careful treatment. Popular comparisons often place a calm green-blue Uranus beside a stormy dark-blue Neptune, then use the pictures as a direct display of internal heat. The intuition is understandable. Convection can carry heat upward, and Neptune's larger internal flux contributes energy to its atmosphere. But cloud images are filtered through chemistry, altitude, wavelength, and time. Voyager's Uranus images looked bland, partly because the visible camera and viewing geometry could not reveal every subtle contrast. Processed modern images at different wavelengths show more structure. Methane absorption can make high clouds stand out. Seasonal changes alter the polar haze. Bright storms can grow and fade. Neptune's great dark spots are not permanent holes or solid marks. They are atmospheric systems. Voyager saw one in 1989. Hubble later watched other dark vortices appear. Some drift toward regions where they dissipate. Bright companion clouds can form as air rises and methane freezes. The two planets do not offer a fixed before and after diagram. Their winds raise another question. If Uranus leaks so little internal heat, how does its atmosphere reach hundreds of kilometers per hour? The answer begins with persistence. A fast wind does not require its full kinetic energy to be rebuilt every second. In an atmosphere with low friction, organized jets can persist. Small but continuous energy inputs can maintain them. Solar heating, even weak at Uranus, is not zero. Internal heat, even low, is not zero. Waves and eddies redistribute momentum. Rotation organizes broad east-west flow. The observed cloud speed also tells us how a tracer moves at one pressure level. It does not immediately reveal the mass of atmosphere moving below or the depth of the jet. A shallow fast flow and a deep fast flow carry very different kinetic energies. Gravity measurements can eventually help with this too. Deep winds rearrange enough mass to affect the gravitational field. At Jupiter and Saturn, close spacecraft data have been used to estimate how far major winds extend. Similar measurements at Uranus would connect weather to interior dynamics. Upper atmosphere temperature also needs vertical context. As pressure falls with altitude, gases expand and cool. Molecules absorb and emit different wavelengths. Methane and hydrogen influence radiative balance. Waves can deposit energy. Far above the clouds, a thermosphere can become unexpectedly hot, even while the tropopause below is extremely cold. There is no single temperature called the temperature of Uranus. The deep atmosphere, cloud-forming levels, stratosphere, thermosphere, and interior occupy different regimes. When a fact sheet gives a minimum near 49 kelvins, it describes a particular atmospheric region, not the center, and not the total heat reservoir. This matters for our central comparison, because a colder visible or infrared layer could arise from radiative chemistry and circulation, even if the deep interior remains warm. Conversely, Neptune's active clouds do not tell us exactly how much energy remains stored at depth. The global internal flux is one of the few quantities that integrates the entire outward journey. It still does not reveal the path. Think of two cities at night seen from orbit. One releases 5 times more light than the other. The difference is real. It does not tell you whether the brighter city has more power generation, less efficient buildings, more people awake, or fewer rules about illumination. You need other measurements. Uranus and Neptune are vastly more complex than cities, but the logic holds. Flux is an output. The cause sits in structure and history. At this stage, we can retire several tempting shortcuts. Uranus is not heatless. Its low internal flux does not prove its center is cold. Its extreme tilt does not prove one giant collision created its thermal state. Its pale appearance does not prove a motionless atmosphere. The word ice does not prove a water-dominated interior. And Neptune's stronger weather does not, by itself, explain the factor of 5. What remains after those shortcuts are removed is more interesting because it is constrained. The two planets carry different thermal memories. To read those memories, the United States planetary science community placed a Uranus orbiter and probe at the top of its list of new large missions for the 2023 to 2032 decade. That recommendation came from the Planetary Science and Astrobiology Decadal Survey, a community process used to set priorities. The wording must be handled carefully. A highest priority recommendation is not the same as a spacecraft on a launch pad. It does not guarantee a launch date. Budgets, technology, mission design, launch opportunities, and agency decisions still determine what happens. As of the evidence used here, the Uranus orbiter and probe is best described as a prioritized mission concept and strategic objective. Its scientific logic is already clear. An orbiter would turn the flyby incision into a time series. Instead of crossing the system once, it could circle Uranus for years. Each orbit could sample a different part of the gravity field and magnetosphere. Close passes could study moons and rings. Remote instruments could map clouds, temperatures, composition, and thermal radiation. The changing geometry would expose both poles and a range of local times. An atmospheric probe would make a different journey. Released before arrival or from the tour, it would enter the atmosphere behind a heat shield, slow, deploy instruments, and transmit measurements until pressure and temperature ended the signal. During that descent, it could measure temperature, pressure, winds, cloud particles, and chemical abundances below levels remote telescopes struggle to reach. Noble gases would be especially valuable because they do not react readily. Their abundances and isotopic ratios can preserve information about the material from which the planet formed. Methane and other species can constrain heavy element enrichment. The hydrogen to helium ratio and isotopes can test atmospheric evolution. No probe could reach the deep interior. Pressures would destroy it long before the central regions. But the well-mixed atmosphere can carry a chemical sample of the planet's building inventory, if the probe descends deep enough to reach representative levels for key gases. The orbiter and probe solve different parts of the inverse problem. Gravity asks where the mass is. Magnetism asks where conducting material moves. Thermal mapping asks where and when energy escapes. Atmospheric chemistry asks what material the planet acquired. Moon and ring observations ask what happened to the local system. None provides a photograph of the planet's birth. Together, they can make many birth stories impossible. Consider the giant impact route again. A collision model that tips Uranus and forms a debris disk should predict something about the Moon's bulk composition and angular momentum. It should predict how heavy material is distributed after the impact. That distribution should affect gravity. If it creates a stable layer, the thermal model should reach the observed flux. If it confines the dynamo, the magnetic model should resemble the measured field. A future mission can test the chain link by link. Now consider the different formation route. If Uranus and Neptune formed from different reservoirs or at different times, their atmospheric noble gases and isotopes may differ. We do not yet have an equivalent deep probe measurement at either ice giant, so the comparison is incomplete. A Uranus probe would provide one anchor. A future Neptune mission would provide the second. This reveals a limitation even in the ideal Uranus campaign. The central question is comparative, but only one planet would receive the new close measurements. Neptune's current internal flux and atmospheric activity are measured well enough to establish the broad disparity. Its deep composition, gravity, and magnetic structure remain uncertain too. A complete twin study would ultimately require sustained investigation of both worlds. That does not reduce Uranus's value. It makes Uranus the first necessary half of a larger experiment. The timing is difficult. The outer solar system is far away. A direct journey takes many years and a large amount of energy. A Jupiter gravity assist can shorten or enable trajectories during certain windows, but those windows depend on launch date and mission architecture. Solar power weakens with distance, so spacecraft may require radioisotope power. Communications delays stretch to hours round trip. Instruments and electronics must operate for a mission lasting decades from development through cruise and tour. The atmospheric probe has one chance. It must survive entry, operate autonomously, and send its data to the carrier or orbiter while descending through an unfamiliar atmosphere. These are engineering constraints, but they shape the science. A launch delay can change arrival season. Arrival season affects which hemisphere is illuminated and how long the mission can observe the approach to equinox or solstice. Orbit choices trade close moon flybys against radiation, fuel, and global mapping. At Uranus, time is an instrument. The planet's 84-year orbit means no human mission can casually wait through every season. The observing sequence must be designed around the part of the cycle available. Earth-based, and space telescope monitoring before and after the mission would extend the context. This is the opposite of the old single snapshot problem. Instead of assuming one encounter is the planet, the campaign would link a close tour to a longer remote baseline. The first frame question for the finished film should reflect that logic too. It should not show a fantasy explosion inside Uranus, or a literal lid trapping fire. The honest visual is a comparison. Two blue worlds, similar in scale, with clearly labeled illustrative heat flows that differ without pretending to be direct photographs. That image would repay the title in one glance. Uranus has heat after all. Neptune is releasing much more. The rest of the film explains why the arrows do not name a culprit. There is a larger consequence, and it reaches beyond the solar system. Planets in the mass range of Uranus and Neptune appear to be common around other stars. Many are detected when they pass in front of their stars or pull those stars back and forth. From those signals, astronomers may obtain radius, mass, orbital period, and sometimes atmospheric clues. If Uranus and Neptune can share similar bulk measurements while hiding different deep structures and thermal histories, an exoplanet with a similar radius is even harder to classify. We may call it a sub-Neptune, mini-Neptune, or ice giant. Each term groups objects by observable scale. None guarantees a common interior. Some may contain thick hydrogen envelopes over rock. Some may contain large, volatile-rich mantles. Some may have lost part of their atmosphere. Some may remain hot from youth. Some may be stratified. Similar radii can emerge from different mixtures, because a small amount of light gas can greatly expand a planet's apparent size. Uranus and Neptune are the only members of this broad family close enough for detailed investigation. Yet they are the giant planets we have explored least. That mismatch gives the five-fold heat difference unusual importance. It is a local warning against universal categories. The 2025 interior models sharpened that warning by finding viable water-rich and rock-rich solutions for both planets. The models do not prove the worlds are rocky magma ocean giants or icy layered giants. They show that current constraints allow a broad range. In 2026, a new preprint pushed one edge of that range further, proposing deep magma ocean-dominated structures for Uranus and Neptune. That idea is intriguing and should be labeled exactly for what it is: a recent model, presented in a preprint, not an established new identity for the planets. Its value in this story is not that it solves the heat disparity. Its value is that it demonstrates how open the interior problem remains. When observations are sparse, model names can sound more certain than the evidence. Water world, rock giant, magma ocean, layered ice giant. Each phrase creates a vivid cutaway. The planet has not chosen a graphic for us. The disciplined response is not to avoid models. Models are how we connect pressure physics, composition, gravity, magnetism, and heat. The response is to keep the cutaway conditional until multiple measurements converge. This principle applies to exoplanets with even greater force. A distant planet's radius may be known to a few percent, while its deep composition remains radically ambiguous. Its age may be uncertain, its atmosphere may be cloudy, its internal luminosity may blend with absorbed starlight. If we cannot infer Uranus's interior uniquely, after a spacecraft flyby and decades of telescope data, we should be cautious when naming a world hundreds of light years away from a transit depth alone. Solving Uranus would therefore calibrate a category used across the galaxy. The mission would tell us how much interior diversity can hide beneath similar mass and radius. It would improve the equations of state used for hydrogen, water, rock, and mixtures at extreme pressure. It would test dynamo models for non-dipolar fields. It would connect formation chemistry to present atmospheric abundance. It would provide a cooling history anchored by an actual nearby planet. Neptune would remain the comparison and the challenge. Perhaps the most important outcome would be discovering that the planets are not endpoints of one neat class. They may be two examples from a continuum of structures shaped by different accretion, impacts, gradients, and atmospheric evolution. The word ice giant would remain useful, much as the word mammal is useful. It would not tell us whether the animal is a bat or a whale. That is the beyond-click gain of the heat mystery. A tiny outward flux, less than the power of a dim lamp across each square meter, forces us to reconsider what kind of planets these are. We can now return to the opening ledger and write what each line truly means. Sunlight reaches Uranus. Some is reflected. Some is absorbed. Infrared radiation leaves. The outgoing total exceeds the absorbed solar energy by a modest amount. That difference is the planet's measured internal heat contribution. The old zero is gone. At Neptune, the same accounting reveals a much larger internal contribution, roughly 5 times the Uranus value per unit area. That difference is real enough to demand an explanation, and not precise enough to name one on its own. What can we say confidently about why? First, low Uranus heat does not require an impossible cooling history. The planet may simply be releasing energy at a restrained present rate. Second, Uranus and Neptune cannot be assumed to share the same interior merely because their sizes and colors are similar. Third, several physical routes can produce divergence. Different formation conditions can establish different compositions. Impacts can alter spin, mixing, and satellite systems. Stable gradients can slow heat transport. Atmospheric condensation can modify convection. These routes can combine. Fourth, no route currently explains every relevant observation so uniquely that the others are eliminated. Fifth, the uncertainty is testable. Gravity, magnetic mapping, atmospheric composition, repeated thermal measurements, and the moons can force the models to make contact with the same planet. That is the complete answer available now. Uranus has internal heat, after all. Neptune releases roughly 5 times more. The low Uranus value may not be the anomaly we once thought. The sharper mystery is why the two worlds arrived at such different rates of cooling. The answer may not be hidden in one catastrophe. It may be written across the entire lives of the planets. Picture the young outer solar system. The Sun is surrounded by gas and debris. Planetary embryos grow, migrate, scatter smaller bodies, and collide. Uranus accumulates one sequence of material. Neptune accumulates another. A late impact tips Uranus, or several impacts reshape it. Heavy elements settle unevenly. One interior develops a gradient that resists mixing. The other remains more convective. Moons assemble, are captured, or are lost. Atmospheres cool. Magnetic dynamos begin. Billions of years pass. The surface evidence becomes quiet. A blue haze hides the deep layers. The original collisions vanish. The disk disappears. The planets settle into distant orbits. But heat keeps moving. Every watt that escapes carries information about the path from then to now. Neptune's larger flux says its path still allows ancient energy to reach space efficiently, or that it retained and now releases a different store. Uranus's smaller flux says its path was different. It may have less heat available at the relevant depths. It may hold more heat behind stable layers. It may transport energy through another architecture. The present measurement cannot decide which. This is why the phrase planetary memory is more than poetry. Thermal evolution is a physical archive. Unlike a crater or a moon, it cannot be photographed in one frame. It is read through energy balance, material physics, and models constrained by everything else the planet does. The archive is damaged and incomplete, but not blank. The 2025 result recovered one line: Uranus is still cooling. The 2026 comparison underlined the next. Neptune is cooling much faster. The next mission, if it is built and flown, would not simply add a close portrait of a distant world. It would try to read the missing pages between those lines. There is a final humility in this story. For decades, Uranus was introduced by an absence. No internal heat, no visible activity. A bland planet knocked on its side. Each phrase contained part of the evidence available at the time. Together, they turned a complex world into a collection of negatives. The planet has slowly escaped that portrait. Clouds appear. Polar structures change. Winds race. A strange magnetosphere is reinterpreted in the context of unusual solar weather. The energy budget rises above zero. Interior models multiply rather than collapse. Uranus did not become more active because we looked again. We became less willing to treat one encounter as a complete biography. Neptune changes role too. It is no longer only the windier, darker, more distant cousin. It is the control case that prevents an easy explanation. Any account of Uranus that cannot explain the difference between them is only half an account. That is why Neptune is the real mystery in the title. Not because we know less about Neptune in every respect. Not because its heat violates physics. Because the comparison removes the comfort of a one-planet exception. If Uranus alone were faint, we could invent a special event and stop. With Neptune beside it, the event must become part of a comparative history. It must show why one planet was mixed and the other layered, why one stored energy and the other released it, why similar masses ended with different thermal paths. the two planets turn explanation into accountability. The final image is the same as the first. 2 square-meter frames float above 2 blue atmospheres. Sunlight enters each. Infrared energy leaves. Above Uranus, a small extra stream rises from within. Above Neptune, the stream is roughly 5 times larger. The arrows do not show a hidden furnace. They do not show an observed wall. They do not show the path of an ancient impact. They show the part we have measured. Everything below the arrows is the investigation. Uranus is not heatless. Neptune is not an answer. Together, they are evidence that planets which look alike can remember entirely different beginnings.